Hi everyone, this is Mr. Lee. In this video, we are starting the series for Gauss's law. And with this video, we're going to define what exactly is this electric flux. Let's begin. So the first thing that we need to go over is the idea of electric field lines. All right, so hopefully by now you have already looked over electric field lines and you know what they're all about. But just in case, here's a definition that we will use. Electric field lines are lines that we draw in space to show the electric field at various points. All right. And a couple of rules for electric field lines. We said that one of the rules is uh, field lines come out of the positive into the negative. Right, that's a big one. Bigger density of field lines means stronger the electric field, which coincidentally means also bigger magnitude of charge. So it could mean that, not always. All right. And another one is, well, the definition or the formula for electric field. For a point, we say the E field is equal to KQ over R squared. That's a big one. And the units are Newton per Coulomb. All right. So a couple of quick little facts about field lines. So now let's go into electric flux. All right. So electric flux. So electric flux has a brand new symbol, and that symbol is a circle with a line, a vertical line that goes straight through it. And we pronounce this as phi, okay? And it's a Greek letter, and it represents flux. And so for electric flux, you might see me write a subscript capital E to show that it's electric flux. Throughout the year, we will do different kinds of flux, such as magnetic flux. And so in that case, that subscript will be different. But most of the times, based on the situation and the problems, you'll know, is it electric flux or is it a different kind of flux? So the idea of flux, well, first of all, flux is an idea, right? It's an idea, it's a concept. And this idea / concept is there to help us explain different parts of physics. And we'll go into the specifics of that. But, spoiler alert, the idea of electric flux will be the crux of Gauss's law. Now, the general definition of flux is the amount of, because we're doing electric flux, E field lines going through an area. All right, I'm going to capitalize area. All right. So electric flux is the amount of E fields going through an area. I'm going to highlight the word area here and E field lines, and of course the word electric flux. Because the things that are highlighted not only is the definition, but it's also the formula that we will later derive. All right. Now, the best way to really give a definition or show the definition of electric flux is with a picture. So I'm going to draw a quick little sketch below. I'm going to call this area a window. So this could be like a window in your room, in the classroom, right? The window is just a window. So let's draw that. There's my window. That's my area. Area of a square, area of a rectangle, right? But the important thing is that it can be physical, right? Like a window itself, or it could just be, if you just put your fingers like that, that's the area too, right? So it is just a area. And the flux or the field lines are going to go through this area like that. I'm going to try my best to do like a 3D representation of this. Okay, so the E field lines going through this window represents the flux. All right, so this image here is electric flux. Now, right next to it, I'm going to write no flux given. So I'm going to draw a window here, right? So if the definition of flux is the amount of E field going through the window, for this image, I'm going to draw the E field not going through the window. In fact, it's going above it and below it, but definitely not through it. Okay, so here there's no flux because nothing is going through that area and nothing is going through that window. And once again, it's important to note that this window, this area, is something that we come up with, and we come up with it to better help and better explain different concepts, more specifically Gauss's law. And finally, let's come up with the formula. Before we do, quick reminder of the definition. Electric flux is the amount of E field lines going through a area. So the formula looks something like this. Flux is equal to the E field dot product of the area. We're going to go over what the dot product represents. So this is the formula that we're going to start off with. There is a different version of this formula on your formula sheet, but we'll get to that later after we explain a couple of more things. Okay, but before we start, let's go over the notation here. You see that arrow on top of my E? That arrow on top of my V is a vector notation. So quick reminder, vectors contain both magnitude and direction. Okay, and we know this because every time we draw a E field line, we always have arrowheads. So my E field here, we can say this is 10 Newton coulombs to the right, right? And the right will be the direction, and the 10 will be the magnitude. And what about this area? So if you think about it, right, the area of a triangle is 1/2 base times height. And if you plug that into your calculator, you'll just get a number, right? But what about direction, Mr. Lee? So the direction's always been there, but the direction for area, if I were to draw like let's say this is like a piece of paper, right? If I were to draw a piece of paper, or maybe even your palm, let's turn that into a palm. So if you hold out your palm like this, this is my left hand, so I'm gonna try my best to draw. That's my thumb, and these are my fingers. I'm gonna be a cartoon character there. All right, so that's my palm. And if this is the area of my palm, I'm gonna highlight the area of my palm a little bit. There we go. This is the area of my palm. And we'll just say the area of my palm is like a rectangle, just to make our math a little bit easier. So the area of my palm is just the length of the palm times the other length. So length times length. So where does the direction come from? Well, if you think about it, if you hold your palm outwards and I ask you, what direction is your palm pointing? You can say, well, if you have your palm like this, it's pointing up. If you flip it upside down, your palm is pointing down. So you can see here that your palm points in a direction. And in terms for a area, the area and the direction of the area is always going to be perpendicular to the surface. So for area, direction is perpendicular to the surface. And this will come up again, so let's put a little star next to that one. Very important. All right, so now that we went over how area can have direction, we went over how E field also has a direction, let's combine those two ideas with the definition and the formula for electric flux. So here's my example one. If I have a area here, and we'll just make this a rectangle / a square, length times length, and if I have my E field going through this area, okay, so I'm just going to draw a couple of E field lines. Don't want to make it too messy. All right, so I have my E field lines going through this area that you see there. We can see when my E field lines are like this, my flux is 100%, okay, which means all E field goes through area. Okay, and we're going to add to this in a little bit. And so I left a little bit space there. So let's do the next one where we have 0% flux. So here, 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 right? If I have my E field going above and below, for here, we can say, I'll do one right into it too. Okay, it's not going through the window, but it's parallel to it. Here, my flux is 0% or zero flux. No E field goes through the area. Okay, so what about in between? So we know that for here, when it is going directly through it, it's 100%. When it's not going through it, it is 0%. What about in between? So draw my area here, here, like so. And I'm going to draw my E field lines at an angle. Yeah, at an angle. So it's going through the area, but it's going through the area at an angle. So let's put a little notation there. All right, so E field goes through window at an angle. So here we can say the flux for this scenario, it is greater than 0, but it is less than 100 in terms of percentage, right? So only a fraction of the E field can be considered to be flux. And so let's write down only a fraction of the E field is part of the flux. Okay, so we can see here, hopefully you're seeing a pattern that in order for the E field to be considered to be part of the flux, there needs to be a specific orientation, okay? And you might be quick to think that the orientation, right, just visually is perpendicular. And in that case, you would be wrong. And it's a little bit weird because the way we describe it, right, we describe the E field going through the window. And so if we were to imagine, let's say let's say this is the window, but like a side view, okay? And if we were to imagine the E field, right, we can imagine, sorry, this is side view. So here we see that the E field is going through this window, and you might be thinking, well, all I see are 90 degrees, Mr. Lee, okay? You're forgetting the definition of direction for area. So remember, the direction for area is perpendicular to the surface of the area. So I'm going to draw the direction arrows in red. So if this is my surface, okay, the surface is pointing in the vertical direction. So we can see here the direction of the area and the direction of the E field are actually parallel. So direction of area and the direction of E field, okay, these two are parallel. Now that is in terms of math, and the formula for flux actually takes this into consideration. But for the sake of your mental memory, if you're thinking, well, as long as the flux is going through the area, like I'm fine with that, then that's great, right? And so another way to think about it is that not only is the direction perpendicular, so let's write this here over on the side. So direction of area is perpendicular to surface. Okay. Direction of E field is perpendicular to surface. So you see how the two are equal, right? That's what makes it parallel. So if we were to take a look at the side view, right? If this is a side view of the window, we will say that the direction of the arrow or of the area is also perpendicular to the surface, like so. And we can see how the E field is parallel to the direction. So if we were to take a look at this here, right? Same idea. If this is like a side view, okay, and we have none of the E field actually going through the window, right? And we know that the direction of the area is in this direction. We see here that no E field goes through the area, but to be a little bit more specific, the direction of area is perpendicular to direction of E field. Okay, and this is also a big major thing, and this helps us with our mathematical representation of flux. So let's go into this component. Okay, so if we were to draw a side view of this situation, okay, we will draw the E field going at an angle like so. I'm not going to draw too many because I'm going to add to this picture. All right, so those are my E fields, and we know that the direction of the area is perpendicular here. All right, so we know that the parallel component is the only thing that matters. So if we have this E field here, okay, and we know this E field has both a vertical and a horizontal component, we only care about the component that is parallel to the direction of the surface, or yeah, direction of the surface, and it will look something like this. So if we were to break down this E field, I would break it like so, right? We have this part of the E field there, and let's do a different color, and we have this part of the E field there. So between these two E field components, if I were to just label this E field Y and this as E field X, we can say only E field X contributes to the flux because E field X is parallel to the direction of the surface. Or another way to think about it is only E field X is actually going through the window. E field Y is passing it, much like in the second situation here. All right, so with all of that, our actual formula for flux, okay? So we know that flux is E dot A, okay? And that dot product, so that dot product, it tells us if you have a vector, dot product vector, so let's label this dot product. What it gives us is a scalar quantity, so magnitude only, mag only. Okay, so here vector requires direction, vector requires a direction, but if you multiply two things of a vector and you're looking at the dot product, you end up with just a scalar. The direction doesn't matter. And the way mathematically it works out, and that's the whole reason why I went through that, is the formula turns out to be E field cosine of theta times the area. And that cosine theta is showing us what this dot product really represents. So let's go back to these previous examples. So if you take a look here in the top one, we see that the E field, let's do green. So we see that the E field is this direction, and we see that the area is direction. So the angle in between, so your angle is 0 degrees. Okay, and so because the angle is 0 degrees, cosine of 0 gives us 1. So what this shows us is that 100% of the E field can be considered to be part of the flux. So let's go below. Here we see that the E field is going upwards. The direction is going this way. So this is the area, and this angle here is 90 degrees. And a cosine of 90 degrees gives us 0. So this means that 0% of the E field contributes to the flux. And that's where this angle here tells us the amount of flux for the angled E field vector. So only the component of the E field that is parallel to the direction of the area is considered to be part of the flux. And that's how we get E cosine theta A as flux. And that cosine theta, that is all about the dot product. And the other one is called the cross product, but we'll talk about that when we cross that bridge. All right, the only other thing other than this formula here is the units for flux. The units for E field is Newton coulombs, and the units for area is meters squared. So the units for flux is Newton meters squared per coulomb, and that shows us how much E field is going through a area. And that is it. I'll see you next time where we utilize this idea of flux with Gauss's law. See you later. Bye-bye.